Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Laplace Transforms 1 from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. First, Laplace transforms are defined and the first shifting theorem is proved. Then, the conditions for existence of Laplace transforms is stated and formulas for Laplace transform of the derivative and integral of a function are derived. The inverse Laplace transforms are defined and the method of finding inverse transform of a rational function is described. Next, solution of initial value problem using Laplace transforms is described. Let us begin with an introduction to Laplace transforms. Laplace transforms provide a very important method of solving initial value problems. The basic premise is to transform a difficult problem into a comparatively easier one. So, we solve the easier problem and then use that solution to find the solution to the original problem. The method is particularly handy for differential equations involving constant coefficients, particularly ones in which inhomogeneous term has a discontinuity. An improper integral, that is, the one in which limits are infinite, is defined through the limiting process. For example, the integral over the definite limits a to infinity function small f of t dt is equal to limit capital T tending to infinity integral running from a to capital T f of small t dt. If the limit is finite, we say the improper integral exists or is convergent. Next, we discuss the definition of Laplace transforms. If f is a function defined for t greater than equal to 0 and s is any real number, then the Laplace transform of f is defined by the integral capital F of s is equal to 0 to infinity e raised to power minus st f of t dt provided the improper integral converges. Please note that it may happen that the integral exists for some but not all values of s. In that case, the Laplace transform is defined only for those values of s for which the integral exists. Laplace transform can be regarded as a linear integral operator which transforms the function small f into the function capital F. Thus, we may write capital F is equal to Laplacian of small f or Laplacian of small f of s. The second form is used when the variable has to be specified. The functions small f and capital F form a pair under the Laplace transformation and are often written as Laplace transform of small f gives the function capital F and the inverse Laplace transformation of function capital F gives the function small f. Next, we take up some simple examples. Example 1, we consider f of t is equal to 1. Now, the Laplacian given by function capital F of s is equal to integral 0 to infinity e raised to power minus st dt, which is specified as 1 by s if s is greater than 0 and infinity if s is less than equal to 0. Equivalently, we may say that Laplacian of 1 is equal to 1 by s for s greater than 0. Now the next example where f of t is equal to t. Its Laplace transform defined as capital F of s is equal to integral 0 to infinity e raised to power minus st t dt. This is equal to 1 by s square for s greater than 0 and is infinity if s is less than equal to 0. Laplace of t is equal to 1 by s square for s greater than 0. Example 3, we take up f of t is equal to e raised to power alpha t. Now its Laplace transform function capital F of s is equal to 0 to infinity e raised to power minus st e raised to power alpha t dt. This is equal to 1 by s minus alpha for s greater than alpha. Thus, Laplace of e raised to power alpha t is equal to 1 by s minus alpha for s greater than alpha. We next discuss the linearity of Laplace transform. Laplace transform is a linear operator. Let us prove it. Let a and b be constants and small f and g be two functions. Then Laplace of af plus bg is equal to integral going from 0 to infinity e raised to power minus st into within the brackets af plus bg bracket close gt. This is equal to a times integral going from 0 to infinity e raised to power minus st f dt plus b times 0 to infinity e raised to power minus st g dt. This is equal to a times Laplace of function small f plus b times Laplace transform of function small g. Hence, the theorem of linearity is proved. Example, f of t is equal to sine hyperbolic of t. Using the linearity property, Laplace of sine hyperbolic t is equal to Laplace transform of e raised to power t minus e raised to power minus t by 2, which gives 1 by 2 times Laplace transform of e raised to power t minus e raised to power minus t. This gives us Laplace of sine hyperbolic t is equal to 1 by 2 within the brackets 1 by s minus a minus 1 by s plus a, which gives a by s square minus a square, provided s is greater than modulus of b. We now prove a very useful theorem on Laplace transforms, which helps us find Laplace transform of a function from that of other known transforms. The first shifting theorem states that if capital F of s is equal to integral 0 to infinity e raised to power minus st small f of t dt is the Laplace transform of function small f of t for s greater than s naught, then function capital F of s minus a is the Laplace transform of e raised to power at f of t for s greater than s naught plus a. We now prove it. In the above equation, we replace s by s minus a. Then capital F of s minus a is equal to 0 to infinity e raised to power minus s minus a t small f of t dt for s minus a greater than s naught. This implies s is greater than a plus s naught. The right hand side of this equation can be written as function capital F of s is equal to Laplace of function small f of t, which implies function capital F of s minus a is equal to Laplace of e raised to power at function capital F of t. We now take up an example where f of t is equal to t into e raised to power alpha t. In the above theorem, we put f of t equals t. Then Laplace of e raised to power at into t is equal to 1 by square of s minus a, where s is greater than a. Next, we discuss the existence of Laplace transforms. The Laplace transform of a function ft will exist provided the integral 0 to infinity e raised to power minus st f of t dt is convergent. It may happen that the integral is convergent for all s, for some s, as was the case in most of the examples cited above. or it may happen that the integral diverges for all values of s. In that case, the Laplace transform of that function does not exist. As an example, the integral going over the limit 0 to infinity e raised to power minus st into e raised to power t squared dt is divergent for all s. Hence, e raised to power t square does not possess a Laplace transform. Roughly speaking, we can see that though as t tends to infinity, e raised to power minus st tends to 0 for s greater than 0, but e raised to power t square diverges even more rapidly. However large s may be, ultimately as t increases, t square minus st will become positive and integral will diverge. Thus, it all depends on the properties of ft for large t whether the Laplace transform will exist or not. A function small f is said to be of exponential order s0 if there are constants capital N and capital T such that modulus of small f of t is less than equal to capital N e raised to power s0 t, where small t is greater than capital T. The theorem about existence of Laplace transform states that if the function small f is piecewise continuous on interval a to infinity, then the Laplace transform Laplacian of small f is defined for s greater than s0. Note that this condition is sufficient but not necessary. For example, the function t into e raised to power t square cos of e raised to power t square is not of exponential order, yet its Laplace transform exists for s greater than 0. We consider an example of a piecewise continuous function. Function small f of t is defined as 1 if the value of t lies between 0 to 1 and it is equal to e raised to minus t if t is greater than equal to 1. The Laplace transform for this function is integral going from 0 to 1 e raised to power minus st dt is equal to 1 minus e raised to power minus s by s for s not equal to 0 and is equal to 1 if s is equal to 0. Integral going from 1 to infinity e raised to power minus st into e raised to power minus t dt is equal to e raised to power minus of s plus 1 divided by s plus 1 for s greater than minus 1. We can write the Laplacian capital F of s is equal to integral going from 0 to 1 e raised to power minus st dt plus integral going over the limits 1 to infinity e raised to power minus st e raised to power minus t dt. Hence, capital F of s is equal to 1 minus e raised to power minus s by s plus e raised to power minus s plus 1 by s plus 1 for s greater than minus 1, where s is not equal to 0 and is defined as 1 plus e raised to power minus 1 for s equals to 0. In view of application to solution of differential equations, we need to know the transform of derivative of a function. This is provided by the following theorem. The theorem states Laplace of small f is the Laplace transform of function small f. The Laplace transform of the derivative is given by Laplace of small f prime of s is equal to s times Laplace of small f of s minus f of 0, where small of s is greater than 0. Next, we prove it. Take Laplace of f prime of s. This is equal to 0 to infinity integral e raised to power minus st f prime of t dt. This may be simplified to give e raised to power minus st f of t with the limit substituted as 0 and infinity plus s integral over the limit 0 to infinity e raised to power minus st f of t dt. This is equal to s times Laplace of function small f of s minus function small f of 0. Hence, the theorem is proved. By induction, we can find the transform of higher derivatives. For example, Laplacian of double derivative of f of s is equal to Laplacian of the derivative of f prime of s. This is equal to s times Laplacian of f prime of s minus f prime of 0, which gives on parts by integration by parts we get s times within the curly brackets s into Laplacian of small f of s minus f of 0 curly brackets close minus f prime of 0, which gives s square Laplacian of f of s minus s times f of 0 minus f prime of 0. Next we study the transforms of integral. Since integration is the inverse of differentiation and Laplace transform of f prime t is essentially the transform of ft multiplied by s, we can foresee that the transform of the integral of ft will be the transform of ft divided by s. In this regard, we have the following theorem. The theorem states, let f of t be a function whose transform exists for s greater than s naught. Then Laplacian of 0 to t integral f of u du is equal to 1 by s Laplacian of f. Now we prove it. Let function capital F of t is equal to integral over 0 to t f of u du. This implies function capital F prime of t is equal to small f of t. Then Laplacian of function small f of t is equal to Laplace of function capital F prime of t. This is equal to s times Laplacian of f of t minus function capital F of 0. But function capital F of 0 is 0, which implies Laplacian of small f of t is equal to s times Laplacian of function capital F of t, or we may say Laplacian of within the curly brackets integral going from 0 to t f of u du curly brackets close is equal to 1 by s times Laplacian of small f. Hence, the theorem is proved. Let us now discuss the inverse Laplace transforms. If function capital F of s is the Laplace transform of function small f of t, then the function capital F of s is equal to Laplace of function small f, which is equal to integral going from 0 to infinity e raised to power minus sg f of t dt. Then function small f is the inverse Laplace transform of function capital F. F can be written as small f is equal to Laplacian inverse of function capital F. Evaluation of inverse Laplace transform is difficult as it involves evaluation of a contour integral. So given function capital F of s, small f of t can be evaluated by use of Bromwich inversion formula, which says function small f of t is equal to 1 by 2 pi iota into integral going from the limits gamma minus I infinity to gamma plus I infinity function capital F of s e raised to power sg ds. Here gamma is a real constant and the contour runs along a straight line from gamma going from minus iota infinity to plus iota infinity. The contour gamma must lie to the right of all the singularities of function capital F of s. If all the singularities consist of poles, the integrals can be evaluated by method of contour integration. Since gamma is towards the right of all the singularities for t less than 0, we close the contour from the right. Then there are no singularities inside the closed contour and we have the expected result. F of t is equal to 0 for t less than 0. For t greater than 0, we close the contour from the left and then from residue theorem we get f of t is equal to summation over I going from 1 to n residue of within the brackets function capital F of s into e raised to power st brackets close at s is equal to s1, s2 and so on till sn, where s1, s2 till sn are the end poles of capital F of s. Let us now look at a particularly simple example to illustrate the method. Function capital F of s is equal to 1 by s minus 1. This function has a pole at s is equal to 1. So, gamma is greater than 1. Hence, from the above formula, we have small f of t is equal to residue of e raised to power st divided by s minus 1 at s is equal to 1. This implies function small f of t is equal to e raised to power t for t greater than 0. The result is expected since we have already seen that Laplacian of e raised to power alpha t is equal to 1 by s minus alpha for s greater than alpha. We will now study the linearity property of the inverse transforms. The linearity property of the inverse transform follows from that of the Laplace transform. Thus, we have the inverse Laplace transform of a times capital F plus b times capital G is equal to a times the inverse Laplace transform of capital F plus b times inverse Laplace transform of capital G. We take up an example now. Take capital F of s is equal to 2 by s plus 1 plus 3 by s square plus 1. Now, inverse Laplace transform of 2 by s plus 1 plus 3 by s square plus 1 is equal to 2 times inverse Laplace transform of 1 by s plus 1 plus 3 times inverse Laplace transform of 1 by s square plus 1. This is equal to 2 times e raised to power minus t plus 3 times sin t. We next take up the case of inverse transform of rational functions. The inverse transform of the rational function capital P of s divided by capital Q of s exists if the degree of the polynomial capital Q of s is more than that of capital P of s. In simple cases, the inverse transform can be obtained by partial fractions. Example, let us find inverse transform of function capital F of s is equal to s plus 1 divided by s square minus 3s plus 2. We make the partial fractions of the above function and we get function capital F of s is equal to s plus 1 by s square minus 3s plus 2 is equal to s plus 1 divided by s minus 2 into s minus 1, which can be written as 3 by s minus 2 minus 2 by s minus 1. Hence, inverse Laplace transform of function capital F is equal to inverse Laplace transform of 3 by s minus 2 minus 2 by s minus 1, which is simplified to get 3 times inverse Laplace transform of 1 by s minus 2 minus 2 times inverse Laplace transform of 1 by s minus 1. This gives inverse Laplace transform of capital F is equal to 3 into e raised to power 2t minus 2 into e raised to power t. We will now apply Laplace transforms to find the solution of initial value problem for linear second order equations with constant coefficients. For this, we will use the theorem on the Laplace transforms of the derivatives of functions. We have the initial value problem y double prime plus py prime plus qy is equal to function small f of t, where y of 0 is equal to a and y prime of 0 is equal to b. To solve the initial value problem, we take the Laplace transform of both the sides. So, Laplace of y double prime plus py prime plus qy is equal to Laplace of y double prime plus p times Laplace of y prime plus q times Laplace of y. This is equal to Laplace of a function small f of t, which is equal to the function capital F of s, where the function capital F is the Laplace transform of function small f. Now we use the result on the Laplace transform of derivatives and the initial values given. So, Laplacian of y prime of s is equal to s times Laplacian of y of s minus y of 0. This is equal to s times Laplacian of y minus a. Another Laplacian of y double prime of s is equal to s square times Laplacian of y of s minus y prime of 0 minus s times y of 0. This is simplified to get s square times Laplacian of y minus b minus as. Hence, Laplacian of y double prime plus py prime plus qy is equal to s square times Laplacian of y minus b minus as plus p times within the brackets s into Laplacian of y minus a brackets close plus q times Laplacian of y is equal to function capital F of s. Or I can write Laplacian of y is equal to function capital F of s plus b plus as plus ap divided by s square plus ps plus q. On taking the inverse Laplace transform, we can have the required solution, which is given by y is equal to inverse Laplace transform of capital F of s plus b plus as plus ap divided by s square plus ps plus q. Thus we see that the Laplace transform method can be used to solve linear differential equations with constant coefficients. The most useful aspect is that it finds the particular solution of an initial value problem directly without solving for the general solution first. Indeed, it usually takes more effort to find the general solution of an equation than it takes to find a particular solution. Also, the same method works for homogeneous as well as non-homogeneous equations, though for homogeneous equations it is not of a particular use. Let us illustrate the procedure by an example. We solve the initial value problem given by y double prime minus 3y prime plus 2y is equal to e raised to power 3t, where y of 0 is equal to 1 and y prime of 0 is equal to 1. We take the Laplace transform of both sides of the above equation. Thus, Laplace of y double prime minus 3y prime plus 2y is equal to Laplace of e raised to power 2t, which gives 1 by s minus 3. Now we use the result on the Laplace transform of derivatives and the initial values to get Laplace of y prime of s is equal to s times Laplace of y minus y of 0, which gives s times Laplace of y minus 1, or Laplace of y double prime of s is equal to s square times Laplace of y of s minus y prime of 0 minus s times y of 0, which can be written as s square times Laplace of y minus 1 minus s. Hence, s square times Laplace of y minus 1 minus s minus 3s times Laplace of y plus 3 plus 2 times Laplace of y is equal to 1 by s minus 3. This implies Laplace of y is equal to, within the square brackets, 1 by s minus 3 plus s minus 2 brackets close multiplied by within the square brackets 1 by s square minus 3s plus 2. This is equal to s square minus 5s plus 7 divided by s minus 3 into s minus 2 into s minus 1. This can be simplified to get the Laplace of y to be equal to 1 by 2 times 1 by s minus 3 minus 1 by s minus 2 plus 3 by 2 times 1 by s minus 1. Thus, on taking the inverse Laplace transform, we obtain the solution y is equal to inverse Laplace transform of 1 by 2 into 1 by s minus 3 minus 1 by s minus 2 plus 3 by 2 into 1 by s minus 1. This is equal to 1 by 2 e raised to power 3t minus e raised to power 2t plus 3 by 2 e raised to power t. So students, let us summarize what we have learned in this module. We defined the Laplace transform of a function and proved the first shifting theorem. Next, we state the conditions for existence of Laplace transform of a function and derive formula for Laplace transform of the derivative and integral of a function. Then, we define the inverse Laplace transforms and describe a method of finding inverse transform of a rational function. Next, we describe method of finding solution of the corresponding initial value problem using Laplace transforms. Thank you students for your attention.